everyone, I'm Iacopo and I'm a James MacDonald Foundation postdoctoral fellow at Central European University. Novelties are part of our daily life, and a way in which we discover new objects or adopt new products can be seen as an exploration of an abstract space in which we sequentially adopt new items that can be therefore put in a sequence. So you can think of people listening to songs, so you listen to a sequence of artists, you can switch between different artists, and from time to time you go back and listen to your favorite tunes. So the first appearance of an artist that represents a novelty, and these sequences are clearly not random. In fact, the dynamics of novelties in these and many other systems appear to obey, for example, the well-known Hipps law, which is power law growth of the number of distinct symbols in a sequence of length t. In this case, the exponent beta quantifies the pace at which we discover new objects. And many models have been proposed to replicate these and other mechanisms, for example, earned models with replacement or biased random walk models. While both these classes of models can recreate the basic footprints of empirical processes, there are two main ingredients which are missing. One is the heterogeneity in the pace of the individual explorers, so some might be more keen to the adventures and others might be what we call exploiters, for example. The other bit, which is crucial, is the benefit brought by social interactions, which are completely neglected, while we have actually strong empirical evidence that social influence is a thing and peer pressure matters a lot. So in this lecture, what we propose is to couple different discovery processes together, and by doing this, we will recover the heterogeneity in the pace of exploration. So the framework is the one of the urn model with triggering, when we have an extraction of balls of different colors from an urn, where a color represents a symbol or an album, for example. So let's say you extract a red ball, and you put it back in the urn together with raw additional copies of it. This is the reinforcement parameter. Then since red is new for you, this also opens up new possibilities. This is what we call the adjacent possible in the space of concepts. That means that you add balls of brand new colors into the urn. What we do here is to couple urn processes together through a social network in a way that you can be inspired by your peers, the neighbors around you in the network. By doing so, for example, urn 1, the process of the urn 1 can get access to the unique colors belonging to the urn of node 2. This is what we call the adjacent possible in the social space. We put these, of course, on the most famous social networks of all times, and you see that we can recover the heterogeneity in the pace of the individual explorers as given by the Hipps exponent. So here the color scale gives you the speed at which the urn discover new items. Notice that here all urns have identical set of parameters. So what we see, the difference that we see is completely due to the connection between the agents. To understand the relevance of the centrality, which seems to be crucial in this case, we devised an analytical approach that matches the simulations, which is system uncoupled ODEs. And you can see from here that while asymptotically all the urns behave the same, so you have the same asymptotic exponents for all the urns, which is given by a combination of the model parameters and the leading eigenvalue of the adjacency matrix, a function of the adjacency matrix. What actually happens is that the transient times, which is actually the regime where we all operate in, the transient times, it's completely governed by the eigenvector centrality. So the Bonacic eigenvector centrality can be used as a proxy for the speed of discoveries. And you see here, I'm plotting the same graph. Again, this time the color is given by the eigenvector centrality that correlates perfectly with the Hipps exponent. Of course, when we move to generic graphs, you need to extend this from the eigenvector centrality to the alpha centrality. And we did this for a bunch of empirical networks, and you see that you have high Sperman-Ranks correlation coefficients in all cases. So to sum up, when you let individuals interact through complex urn models coupled on a network, you can recover the heterogeneity in the pace of individual explorers. And through the analytical approach, we can see that asymptotically and at transient times, the ranking induced by the Hipps exponent is persistent, and the centrality of the explorers can be a proxy for the pace of discovery of the different individuals. If you want to know more, you have the references down there. Here you have a light reading written for Nature Italy by Michele Traverso. I would like to thank my collaborators over there, you for listening. If you have questions, you can, I guess, write me here in the chat or drop me an email. Thank you.